Algebra 1, Lesson 112, we are graphing and solving systems of linear and quadratic equations. Now, we have solved systems of linear equations quite a bit by this point through graphing, through algebra, and today we're going to be looking at not just linear equations, but if I had a line and if I had a parabola. So it's going to be very similar to what we've done in the past. So let's start with what we've done in the past. Graphing two lines, in this case, 14 minus 4x and x plus 4. Let's see where they intersect. So let me make this a little bit bigger. And let's start off with that 14 minus 4x. So we go to our y-intercept and then go down 4 over 1, down 4 over 1, down 4 over 1. All right. So we can see my line. Remember to be as precise as you can with this, especially when we are graphing. It's going to be tough for me to show perfect lines, but grab a ruler while you're doing them on your graph paper. And then we have my other line, x plus 4. So we start with my y-intercept of 4, and then we have a slope of 1. So up 1 over 1, up 1 over 1, all the way across. And we have this nice line that we see does intersect right here at, it looks like 2, 6. Now remember that we can always check our work with these graphs by plugging them back into their original equations. And we say, does this work? 6 equals 14 minus 4 times 2. Well, that's 6 equals 14 minus 8. So yes, 6 equals 6. Worked for one, has to work for both. We plug it in again and we say 6 equals 2 plus 4. Yes, 6 equals 6. So it does actually work. That is our solution. We're going to be looking for the same thing here with a quadratic and a linear function, but we might actually end up with two different intersection points, considering the parabola is a curve. So let's start with that y equals x squared. You can make a table, you can use our method for graphing your quadratics, but by this point you should probably be pretty good with this parent function. Saying it starts at 0, 0, we have 1, 1 and negative 1, 1, 2, 4 and negative 2, 4, and then we have 3, 9 and negative 3, 9. Take some time to make sure you have a really nice curve on your parabola rather than a kind of a V shape. It really is more of a U shape. And then we have x plus 6. So we have that y-intercept at 6 and then a slope of 1. So up 1 over 1 all the way across. And we can go down 1, left 1 all the way across. And you can actually see some of those intersection points already. Really nice intersection points, actually. So it looks like we have one up here at 3, 9. We have one over here at 2, negative 4. Well, with this actually, we can check, but both of these are going to be solutions to this system of equations. We can plug them in. So we'll start with this 2, negative 4, and with y equals x squared, I plug it in and we say oops, I turned that around. Oops, sorry about that. And we have negative 2, 4. That would make a lot more sense. All right, so if I have a positive 4 for y, a negative 2 for x, yes, 4 equals 4. So that works. And then y equals x plus 6. 4 equals negative 2 plus 6. Yep, that works. So for sure, that is one of our solutions. And then we check 3, 9. It works for y equals x squared, and it works for y equals x plus 6. So yes, both of those are solutions to our system. All right, let's try another one. We have another one that is just a regular parent function of our quadratic. So x squared, just going to do this very quick on our page, and you can do it. Pause the video and make sure that you have your parent function nice and neat. Draw that nice smooth curve. And then we can graph y equals 2x minus 1. So it starts at negative 1, and then we go up 2 over 1. Here, let me just change colors. It'll help. So here we go. Up 2 over 1, up 2 over 1, up 2 over 1. All right, and here is our line. As you notice, this one doesn't cross through the parabola, it just touches the parabola, just in one point. So it looks like our only solution to this is at 1, 1. And we can plug it in. It's definitely going to work here. 1 equals 1 squared, that's true. And 1 equals 2 times 1 minus 1, and that is true. 1 equals 1. So we actually only have one solution, and that is definitely a possibility. We could have parabolas that look like this. Here's our parabola, and we have two distinct crossings. We could have a parabola where it just touches once, and we could also have a parabola that it doesn't touch at all. That's a possibility too. So we can have any of these possibilities, 0, 1, or 2 different intersection points. All right. Systems of equations, here we have 2x squared minus 9. I'll let you try this one out and think about it. So pause the video, try it out for yourself first, okay? But here in just a second I will show it, but take some time, graph this quadratic, and make sure that you get it correct. So now I'm going to graph it here, and I'm going to use our method that we have learned in past lessons in order to do this. So let's find the axis of symmetry, so x equals negative b over 2a. Well, my b is, well, it looks like it's gone, but it's actually 0. So negative 0 over 2 times 2 is just 0. So when we plug it in, I get 0, negative 9 as my vertex. So I go down here to negative 9. Well, ends up that that is also my y-intercept, so I'm definitely going to want to plug in a few more points. Let's say I plug in x equals 1. So 2 times 1 squared minus 9, that is just 2 minus 9, so negative 7. So I have a point at 1, negative 7, and since this y-axis is my axis of symmetry, I can flip it over and I have negative 1, negative 7. Let's say I plug in x equals 2. I want another point. 2 times 2 squared minus 9. So that's 2 times 4 minus 9, or 8 minus 9. So I have negative 1. And I can flip it over here to have negative 2, negative 1. And we can see that my parabola, it's a little bit skinnier than our parent because of that 2 in front of my x squared. And it's shifted down 9 from that y-axis being negative 9. Now I have also a linear function, which I am going to graph here in lime green, and we also start at negative 9 as my y-intercept. But in this case, I have a slope of 4, so I go up 4 and over 1, up 4 and over 1, up 4 and over 1. And here is my line. And it looks like it does actually cross in 2 distinct points. It looks like it crosses here at 0, negative 9. It also looks like it crosses here at 2, negative 1. Well, we can check both of these, but you will see when you plug them in and check that both of them are solutions to the equations. All right. So what we can do here is with a graphing calculator, you can also do this. Now, I'm not going to show this with a graphing calculator because it would look familiar because it's actually the exact same process that we do to graph systems of equations, linear equations, and find the intersection point. So if you need a refresher, go back to that lesson that we looked at graphing systems of linear equations, and with that graphing calculator in that lab, we will do the exact same process here, which is using the calculator's ability to find the intersection of 2 points, and it'll work the same way for these quadratics and linear equations. So go back to that lesson, check out the lab that we did for that, and you can check your solutions for these, or you can do that by hand because they're not too difficult to look at. Now, yes, we can do it by graphing, but sometimes we don't end up with really nice numbers. So algebraically is another way to go. And just like we learned with linear equations, not that difficult. We're going to use substitution this time, just like we would with linear equations. We have one of the variables by itself, and we can plug in the information. So I'm going to plug in 5x plus 3 into this y, so that I have 5x plus 3 equals x squared plus 5x minus 1. And then I need to get all of my variables on the same, all of my everything on the same side to solve for x. This goes back to our skills of solving a quadratic equation by algebra. So I'm going to subtract 3 and subtract 5x, so I have 0 on one side. And I do the same on the side minus 3 minus 5x. I end up with x squared, those go away, minus 4. And then, like we've learned, I'm going to factor. In this case, this is a difference of squares. I get x minus 2 and x plus 2. If I have my zero product property, I'm saying this could be 0 or this could be 0. So if x minus 2 equals 0 and x plus 2 equals 0, I can solve and say x could be 2, x is negative 2. And I can plug them in to find my my intersects, because these are not actually the zeros of the function, these are the x coordinates of my system of equations solutions. So I plug them in. Now I'm going to use the linear equation. It's a lot easier. And we say y equals 5 times 2 plus 3. So y in this case would be 13. So one of my solutions is 2, 13. And my other one, y equals 5 times negative 2 plus 3. That's negative 10 plus 3, so y equals negative 7. So I have another point of intersection at negative 2, negative 7. And we could, of course, plug that back into the quadratic to confirm. But by substitution, we can definitely prove that we have these two solutions. All right. And then we could do that for this one here. I'm going to plug in right here and substitute 2x minus 3 equals x squared plus 7x plus 3. Subtract 2x, add 3. And we get 0 equals x squared plus 5x plus 6. And I factor. This is just one of our regular add to 5, multiply to 6. So I get x plus 2 and x plus 3, which means that x must be negative 2 and negative 3. I plug those in to find my y coordinates. So y equals 2 times negative 2 minus 3. So y equals negative 7. And then I plug it in for negative 3. So here's my 1 point, negative 2, negative 7. And then I plug it in for negative 3. Y equals 2 times negative 3 minus 3. So negative 6 minus 3. So y equals negative 9. So I have my 2 points of intersection here at negative 2, 7 and negative 3, negative 9. So for the second set, those are my 2 intersection points. All right. So after all of this, we can put this into some context. And your book will actually show graphing of this. Since they're really big numbers for this problem, I'm not going to graph them, but you absolutely can in order to show this. I'm going to do it algebraically. And this will be our last one in the lesson. I'll show you some other ones that you can practice with, that you can do on your own and check with a graphing calculator. But we'll say this is our last one for this lesson. So, a ski patrol fires an explosive arrow to trigger an avalanche. The path of the arrow is modeled by the equation y equals negative x squared over 1600 plus 2x. And the shape of the mountainside is y equals 3x over 4, where x is the horizontal distance and y is the vertical distance. And what altitude will the arrow strike the mountain? So we are in feet here. What this is looking like is we have this mountainside that is shown by y equals 3/4 x. And then we have this arrow also starting, what we're saying is at 0, 0. So this mountain starts at 0, 0, and this arrow starts at 0, 0, but it has a quadratic path. That wasn't a great quadratic, sorry about that. But we are saying, where does it hit the mountainside here? If this is y equals negative x squared over 1600 plus 2x, where do these intersect? And we say, of course, they're going to intersect at 0, 0. That's implied since this one, the linear equation, has a y-intercept of 0, 0, and so does our quadratic, but that's not the point. The arrow isn't going to strike the mountainside right there. We want to know, higher on the mountain, where does it strike? So I'm going to solve this algebraically You can definitely do it by graphing, but you just need to be very, very precise. So we have these already in with y by itself, so I'm going to go ahead and plug in and say 3x over 4 equals negative x squared over 1600 plus 2x. And I need to get it equal to 0 on each side. I'm actually going to put everything on this side. So add x squared over 1600 and subtract 2x. Gets us x squared over 1600 minus, well, that 2x is 8x over 4. So minus 5x over 4. You can check all of that out, but all I did was get some common denominators. Now I need to factor, and when I look at these, actually, I can factor out an x. But to make this even easier on myself so that I don't have to be working with denominators, or with all denominators, I'm actually going to take out an x over 4. That will get rid of the denominator on this second term. I get x over 400, you can check that for yourself, make sure it's the same as x squared over 1600, and then minus 5x. Oops, sorry, that x is no longer there, it's just minus 5, equals 0. Which means that I have two pieces here that I can actually solve for 0. X over 4 could equal 0, and x over 400 minus 5 could equal 0. Well, this one on the left gives me that x-intercept, or that origin point, because x equals 0, and when we plug it in, y will equal 0. But that's not really the one we want. We want the second one here. And I'm going to solve for x by adding 5. We get x over 400 equals 5, and then we're going to multiply by 400 on each side. Ends up giving us x equals 2,000. And we're in feet, of course, but we need my y coordinate as well. So I'm going to plug it into the y equals 3x over 4 and say y equals 3 times 2,000 divided by 4. That's 6,000 over 4, so y is 1,500. What that means is this point of intersection up here where that arrow is going to actually hit the mountainside and create the avalanche is at this coordinate point of 2,000 feet by 1,500 feet. And that's where the arrow is going to strike the mountain. And you will see that when you graph it as well. But that's how we would go about this algebraically. Now, I'll just show you a couple more. Pause the video and try these for yourself so that you can check them. But here's another one very similar to what you did above by graphing or by substitution. And then there's a couple more practices here for just graphing these different ones and finding those intersection point or points. Okay, I'll just show this one really quick. If I have my quadratic looking like this, and then I have a horizontal line, y equals 4, that's a pretty fun one to do. Think about how quickly you could figure out what those intersection points are. Okay, here's another one. Think about if this one has a quadratic like this, and then we have a line that starts at -4 and goes negative here. This is a possibility of one where maybe we don't have an intersection point, maybe we do, maybe it's only one, but it's going to be kind of close. Okay, so try that out. See where they intersect, be very precise, much more precise than what I was doing, but you can see, but it kind of starts off looking like it might not have an intersection point. Then here's some more graphing calculator problems that you can try. All right, well, I hope this helps for your homework and your studying.